Now that we have a cutter HDA set up to create our slicing geometry, we can run some Boolean fractures pretty quickly and easily. You can just drop in either the Boolean shatter or Boolean fracture sup. I'll grab Boolean fracture in this case, and we'll connect our original geometry to that and our cutters. And then if we display that, we'll turn the template view off of the original geo and drop in an exploded view to take a look at the fracture. You can see that we're starting to get some pretty nice and realistic details that look pretty convincingly like concrete. However, this is a pretty simple example where we're just fracturing up one piece of geometry, and in a typical production situation, there are some other things that we'll have to consider. The four main things we'll be focusing on in this video are how to optimize the Boolean cutting process, how to handle the naming of the pieces, how to deal with multiple objects being sliced at the same time, and how to make sure that you can fracture the same geometry multiple times successfully. And because we need to set up more functionality than the Boolean fracture provides on its own, this is another good example of where we can set up an HDA to streamline the process so that we don't always have to set it up by hand. Now, as I mentioned, one of the things that we'll take a look at is fracturing multiple objects. So let's give ourselves multiple objects to work with. Let's drop in a copy and transform node, turn it up to perhaps 10 copies, and let's raise them all upwards in Y. Of course, I have to display that first. Raise that value, and I'm going to leave a little bit of overlap on those pieces here. And then I'll connect that copy node to our Boolean fracture and the cutter generator. And let's take a look at the cutter generator results. You can see that this resolution is now stretched over a much larger area because we're using a fixed grid size in that cutter resolution parameter there. So typically you'll have to compensate with those settings by adding a bit extra resolution and perhaps an extra subdivision or two on this add mesh subdivisions parameter there. Now, sometimes when you fracture multiple objects all together like this, it'll work fine if we just run our Boolean fracture and let that cook for a moment. We can then look at the exploded view, and it looks like in this case it seems to be fracturing correctly. However, that's not always the case. Sometimes when running a fracture on multiple objects at once, perhaps an entire building composed of lots of pieces or a complicated vehicle model, it can cause issues with the fracture process. I suppose that may be due to the extra complexity of multiple overlapping pieces, and if you'd like, you can run a fracture of everything all at once, and if that's not working, then you can switch over to doing the per piece fracture. So to fracture each one of these objects one at a time, we'll need a for each loop. So we'll tab and create a for each, and select for each named primitive. Now, in order for this loop to work, it needs an attribute to iterate over, so each one of these objects will need a distinct value for that provided attribute, which defaults to name, but we don't currently have a name attribute on our geometry. So let's create a primitive name on our pieces. We can use our connectivity that I believe we looked at in some earlier videos. This will detect which pieces are connected meshes, so each one of these sections of building will get a unique integer value from 0 through 9. So on the connectivity node, we'll change this to be a primitive type, connect that to our copy, and we can check the spreadsheet on that just to make sure that's giving us some values to work with. Sure enough, 0 through 9, that's all good. Now let's drop in a primitive wrangle. And in that wrangle, we'll type s at name to create a string name attribute. And I'll call this building section underscore plus I to A, which is a function that will convert an integer to a string so that we can add it to our name here. And we'll pass in I at class. We'll rename that wrangle so that our network stays clean and check the spreadsheet. So now we have building section 0 through building section 9. And maybe in this case I'll get rid of the underscore since we'll be using underscores to separate sections of our names later, as you will see shortly. And it's always good practice to make sure that we're deleting attributes that we no longer need. So if we add a attribute delete sop after our name wrangle node, let's move that loop out of the way. Then on that attribute delete, you can select the class attribute just because we no longer need that. Now if we connect our attribute delete output to our for each loop and display the begin node, you can see it's selecting one of our objects for that current iteration of this loop. And you can see this working properly if you select that end node. Don't display it yet, leave the display on the begin. You can turn on single pass and scrub through the different passes to see it operating on different pieces of your input. However, this is kind of an annoying thing. It seems like when you change this single pass parameter, it doesn't refresh what's happening in the loop, so you often need to hit that reset cached pass option in order for this to update the current pass based on that parameter. This is very helpful for debugging your setups. So now that we have that loop set up, we can connect our Boolean fracture within that for each loop. So we'll just drag that down, connect the for each begin to that first input. Can display the Boolean fracture output. Actually, let's just connect that to the end and view our exploded view. Now this is only showing us one of our fractured pieces because we have that single pass turned on. But if you turn off that single pass option, this will take a moment and it'll run a fracture for each of our pieces. And it looks like it fractured things correctly. And this is a bit more reliable than just doing all of them all at once. However, now that we are only fracturing one piece at a time, we don't need to use this entire mass of cutter geometry to run that fracture. This particular fracture isn't too terribly slow, but these fractures can get a bit slow to process, and it's good to optimize that a bit and remove all of the cutter areas that we don't need. Now you could do a very basic removal using a bounding box of our input geometry, but I'm going to go with a slightly more accurate method of using the VDB based trim that we set up for our cutter geometry network. So let's dive inside a copy of that cutter HDA. So I'll just create one of those in the scene here and dive inside. Actually, before we dive in, right click on that and click on Allow Editing of Contents. Then dive inside and we can select this VDB from polygons and this group selection here and the promote. We don't have to worry about this group copying stuff, but I'll grab that blast node as well. And we'll copy that and jump back out to our shatter setup. And we'll paste that in here. I'll connect that blast under the promote. We'll connect our cutter geometry to the first input of that group, and we'll connect our for each begin to that first input of the VDB from polygons. I'm just going to detach this Boolean fracture and move it down for now, just to make our network a little bit more clean. And let's move our VDB from polygons over a bit. Now our VDB from polygons is currently throwing a warning here because it's complaining about the expression in our voxel size. In our cutter generator, we were using a reference to the input geometry, and we don't have a null called input geo in our shatter setup, So we'll need to change this to just use input 0 for both x and z and y, like so. And then that warning should go away. And we'll delete this reshape node because that has some references to the main cutter geometry controls, and we'll create a new one, VDB reshape SDF. And for now, I'll just give this an offset of, we'll try 10. So now, if we zoom in on our resulting VDB, you can see we have an expanded representation of the current piece, which is now grouping the cutter geometry and promoting it to prims like we saw before and isolating just that area. Now this will fracture a bit faster than cutting with all of this stuff. So we can connect this updated cutter geometry to our Boolean fracture and connect our input. And then we'll go down to our exploded view to make sure that our entire network is still working properly. Sure enough, looks like our cutting is still good, so we haven't broken anything with our updates. And now we can take a look at our piece naming. Now, one of the nice things about this Boolean fracture node is that it gives you some options for how it handles the naming of the pieces. If we look at that Boolean fracture within the network, let's zoom in on it and pull up the spreadsheet for the names. You can see it's just naming everything piece 0 through, looks like piece 4. This is only a few pieces in this case. And typically, it's good practice to add the new names of your pieces to the existing name of the object. So we have names coming in of building section 0 through 9 that we already set up here. And it's extremely helpful later in the destructive process to know which section each piece came from. So in this case, we're going to switch this name attribute to, instead of overwriting the existing name, we're going to append it. And pull up that spreadsheet again, so you can see now we have building section 9, piece 0. However, to organize our names a bit better, we want to separate the original section name from the new piece names. So let's add a separator character in that name prefix. I'll use an underscore, and this now gives us a better organized name attribute with more clear fractured piece names with the original section names there as well. Now when we make an HDA for this setup, we'll want to change this name prefix every time. So let's create a subnet for everything we just set up here. We can just grab our for each loop, and I suppose the exploded view as well. Hit Shift-C to create that subnet. And you can rename this to something like Shatter with your own custom name for your tools. And then we'll create some parameters for this HDA by going to the gear icon and edit parameter interface. We'll select these input labels and make those invisible. Then we'll add a string attribute and just call this something like name prefix with a nicer label, name prefix with capitalization and spaces. And if you go to channels, we can give this some sort of default value. Just a value of piece works fine. And then you can hit accept, right click on that parameter and copy it. Then we'll go inside our shatter network, select our Boolean fracture, click in the name prefix field, and we'll paste relative references. Now we can delete this piece text in there already. We can leave that underscore, and you'll see that this is putting in a channel reference to our string parameter. It's including these backticks there, which are very important. That means it's going to evaluate some function within these backticks that allows you to put code into any string parameter. It won't put those backticks in your actual name. That's just looking up our name prefix from the tool settings and using that for our updated names here. Now another setting that's very important to create a control for on our Shatter HDA is the detriangulate option. Now I believe we talked about this a bit in the fracture debugging video, but when the Boolean runs, it internally converts your mesh into triangles to do its processing. But then after it's finished, it will detriangulate that to give us this nice and clean mesh end result. However, that detriangulate processing can cause some little problems in the mesh that really only matter if you want to refracture this again. There's nothing wrong with this mesh for simming and rendering purposes. It's really only an issue for refracturing. So if you were to cut this up in 3 passes, you would want to make sure that you have detriangulate set to no polygons for the first and second pass, and then if you want for the final pass, you can set that back to all polygons. Now we have a nice little shortcut for adding this parameter to our HDA without needing to recreate that menu manually. So we can jump out, go to our Shatter HDA, edit parameter interface, and if we go back to our Boolean fracture here, we can just click and drag the detriangulate into this window. This will create just a copy of that parameter with the same default values and menu options and everything else. Under the Channels tab, it also has this linked channels pointing to this underlying Boolean fracture. If we hit apply, then sure enough you can see that's automatically linked our top level control to this parameter on that fracture SOP. Now we're almost done with this Shatter HDA, but we should also take care of the constraints output from this Boolean fracture. If you drop in a null, you can see that that second output there is creating a constraint network based on those fractures. And I don't want to talk about constraints this week. We will talk a lot about those later. But we can use an RBD pack SOP to bundle up the fracture and the constraints together. You can see this tooltip here says the first input of the RBD pack is the geometry, second is the constraints. And if you look at that node detail, then you'll see it has 3 packed geometries. It's for the fracture geometry, the constraints, and then optionally a proxy input for that third input there. Now because we only have one output from our for each, if we didn't use this and we just merged together our fracture geometry and the constraint network, it would mix up all their attributes and it would be a bit messy. But this RBD pack makes sure that it keeps the fracture separate from the constraints, and then when we output everything at the end of the for each, then we can use the RBD unpack to re-separate the fracture from the constraints. So just create RBD unpack, connect our for each output to that, and then we can separate out the fracture geometry and constraints into 2 separate outputs from our subnet. So we can create 2 output nodes, connect the first input to one, second input to the other, and you can see here we have our fracture geometry there, and we have our constraint networks in the other. Now double checking the output for each, I'm seeing that we're actually getting our trim area following through from our cutters onto our final geometry. So this just reinforces how important it is to not keep any attributes or groups on your geometry that you really don't need. So let's go in, kind of do some final reorganization, and we'll go to our cutters. And after doing that trim blast, let's just drop in a group delete. We'll select that trim area, and then make sure that it's gone. Then we can jump out of our Shatter HDA, and then right click and create digital asset. I'm not going to do it because I have a Shatter digital asset already made. And then once you create the digital asset, it's good to right click it again and then tell it to match the current definition so that this copy is in sync with what's on disk.